fill us in on like your take on CPUs versus GPUs and why they're so important in AI research.
Yeah, sure. So let's try to break it down, right? So the way I look at CPUs is that they're the ultimate general purpose machine. They're based on an architecture that existed for a long time called the von Neumann architecture. And the way that CPUs perform computations is that they bring data from an external memory to registers that are local to the CPU, to the hardware circuit that runs the computation. They read registers, perform a computation, and then write the results back to registers. And at least until recent years, these registers were scalars. So think about a single floating point number. The beauty of this architecture is that it can really do anything, and that's why CPUs are used everywhere that you can think of. The downside of this architecture is that there's a lot of overhead in decoding an instruction in order to just multiply two scalars together or something like that. Now, modern CPUs in recent years improved that to some extent with vectorized instructions, but that's an incremental improvement over the fundamental architecture that is there. What GPUs do, so GPUs indeed were, at the beginning at least, were optimized for graphics or for massively parallel workloads.
Mm-hmm.
And graphics was the first use case that kind of led for the emergence of this architecture. And the idea with the GPUs is that the fundamental concept is the same, but instead of using a few very powerful cores, you use thousands of weaker cores. And then if you have a workload that is massively parallelizable, like matrix multiplications or like graphics where you compute a different pixel of an image, then you can parallelize the workload on all these slower or not as powerful cores and perform the computation in parallel and get an end-to-end acceleration. But if I try to tie that back to AlexNet that you mentioned, I think what was interesting about the AlexNet paper was that it was, as far as I know, the first example of using a neural network with a very deep number of layers and with a very large data sets. So basically the leverage of scale in order to achieve state-of-the-art results. In that case, it was for a vision benchmark or workload. And because they scaled the amount of computation needed so aggressively versus previous neural networks, they needed massive parallelization, and they achieved that with GPUs.
Nice. Yeah, and it was a huge achievement. It blew all of the other machine vision models at that time out of the water, and it brought deep learning to everyone's attention. It was something like a 30% reduction in errors relative to the next best model at that time. And so all of a sudden, academics and practitioners alike took notice. And by a year later, all of the top architectures in this machine vision competition were deep learning architectures, whereas the year before, there was just the one. So,
yeah, exactly.
Yeah, all of a sudden, deep learning started to be everywhere. And 10 years later, it really is. And it's mind-blowing what's changed over 10 years. It's mind-blowing what's changed over the last year.
Right. I think it was a mindset shift, by the way. I think that architecture allowed everyone to think that a neural network algorithm can by itself win against all the Taylor algorithms that we built as a community over a decade of vision optimizations and so on. And that actually trailblazed the same exact achievements in other fields as well beyond vision.
Right, totally. So some terms that you used in your description of CPUs versus GPUs, which, I think I would normally just kind of let the person get away with saying them, but I really want to understand what it means, and you can explain it to me. So you talked about CPUs having a small number of strong processors, and GPUs is having a large number of weak ones. So what is it that makes a processor strong or weak? You know what I mean? Like, yeah.
Yeah, definitely. So there's a couple of things to kind of pay attention to, but at the heart of CPUs and GPUs, that there's a hardware data path that we build, and that data path processes instructions. These instructions could be as simple as add or multiply two scalars together, and there's also control instructions or data movement instructions. So think about loading a value from memory or saving a value to memory. Now, that data path runs at a certain frequency. And state of the art CPUs run at a frequency of somewhere around 3 gigahertz. And that basically means that that's the speed in which we do calculations. Now, on top of that, the data path has a bunch of optimizations in order to do multiple computations at once. So it can do multiply, and in parallel to that, load the next value, and in parallel to that, save the previous value, and so on and so on. So that's how I would describe a CPU core. When you go to a GPU core, this main data path is much simpler. It runs at a lower frequency, in order of 1 gigahertz or 1.5 gigahertz. So we're talking about 2 to 3x slower. We don't do as many things in parallel as we do in CPU, but that simplicity is actually beautiful because we can make these cores extremely small in hardware and then pack thousands of them in a chip and get performance that way, given that the workload is parallelizable enough.
Cool. Yeah, thank you. That makes sense to me. So yeah, so these weaker processors, they go more slowly, and they do simpler operations.
Yep.
So I guess that means that like, does it mean that they're like cheaper to make, but they're also maybe smaller, so you can fit more of them into like a given area? Like, for example, like why wouldn't somebody want, like, would it be theoretically possible for somebody to build a GPU full of like 3 gigahertz processors or something?
Yeah, it's a good question. So there's a couple of reasons to that. First of all, these very complex CPU cores or very advanced CPU cores are indeed much larger area-wise, and we do have a limitation on the amount of area that we can build into a single chip. So that's one of the considerations there. The other consideration is that when we run these CPUs at a lower frequency, they're also smaller, as you said, but they can also run at a lower voltage operating point, which make them more power efficient.
Right.
So in some ways, building these small and simple CPUs allows you to run more power efficient and allows you to pack more cores in a single chip.
Power efficient and probably heat as well, right? That's probably
Yep.
a factor. Yeah.
Yeah, they go hand in hand. Yep.